That's what your iPhone might say after today's video, because today we're going to train a mobile object detector to find sharks and fish in images. At the end of the video, you'll have a model that looks a little something like this. One of the most frequent questions I receive is, what sort of prior knowledge and experience do I need in order to be able to build a computer vision powered application? Do I really need a PhD in machine learning? Well, the answer to that question is emphatically no. You don't need an advanced degree, and in fact, sometimes you won't even need to learn how to code in order to get started with computer vision. And that's what this video is all about. We're going to take you from nothing to a trained and deployed computer vision powered mobile application, all using free and open source tools and without writing a single line of code. And while we'll be training our iPhone to identify fish at the aquarium, you can use these exact same steps to solve any number of problems. In fact, we've taught thousands of students, hobbyists, and software developers to use computer vision to train a model for the first time to do everything from protecting endangered species to preventing wildfires. And that's just the beginning. The only limit is your imagination. So if this sounds exciting and interesting, you're in the right spot, because we're about to level you up. All right, so we know where we're heading, but how are we going to get there? Well, we're going to use something called a neural network. And whoa, before you change that YouTube channel, don't worry. This isn't one of those YouTube videos where we all of a sudden jump into a whole bunch of complicated math and computer science gobbledygook. If you're interested in how a neural network works, this is not the video for you. There's plenty of other ones that I'm sure you can find on YouTube. For us, we're just going to use a neural network as a tool. And so all we need to know is, what does it do and how can we use it? So to answer the question of what does a neural network do, we can imagine it kind of like a child learning from flashcards. So if we show a child a flashcard, it's going to see the question on it, and it's going to guess a response. If it's wrong, we say, nope, that's not right. The correct answer is actually this. And over time, after going through those flashcards many times, the children learn what you're trying to teach them. So a neural network's kind of like that. We show it a whole bunch of questions, and it learns to predict the answers. So for us, we're going to show it questions, which are images, and answers, which are the locations of fish in those images. And over a period of time, our neural network is going to learn to match an image and the location of the fish. And so with any luck, it will learn to do that not just by memorizing the exact images that we give it, but also to generalize to any image of fish that we give it so that it can actually be useful for us. So we'll learn a little bit more about that in a bit. But the first thing that we need to do is go collect a whole bunch of images of fish that we are going to use as our examples, our flashcards for the neural network. And to do that, we're going to have to go to the aquarium. Unfortunately, the nearest aquarium is a little bit of a drive, so buckle up because we're about to go on a road trip.
Hey guys, what's up? I'm Brad, one of the co-founders of RoboFlow. We're a startup that makes computer vision accessible to everyone, not just machine learning experts. And we do that in a couple ways. One way is content and videos like this, but we also make software and tools so that you can focus on the problem you're trying to solve, not on reinventing the wheel. And that's where I usually come in. I'm usually behind the keyboard, not the camera. I'm slinging code, not videos. But I finally convinced Joseph and Jacob to let me shoot a YouTube video on one condition. They said I'd only get to shoot another video if we got more than 100 subscribers from this one. So help me out, hit that subscribe button, ding that bell, and hope you enjoy the show.
All right, we made it to the aquarium. So now we're going to go inside and we're going to take a whole bunch of pictures. Remember, we're creating our answer key for our model. So we want to make sure to take a wide range of pictures of everything that we want our model to learn to identify. Alright, I think that does it. We've got a whole bunch of photos of a wide range of critters. Let's go home and see what we've got. Those pictures turned out great. We have the beginnings of a really cool project on our hands. The next step is taking those raw images and turning them into something that our neural network can learn from, the flashcards, if you will. This process is called annotation, and it consists of drawing boxes around all the things that we are going to want our model to recognize. This means the fish, the sharks, the starfish, the stingrays, and any other critter that we find that we want our model to know about. There's a whole bunch of tools that we could use to do this, but we're going to use RoboFlow because it fits really seamlessly into the rest of the process, as we'll see later. So to get started, I just go to roboflow.com and click Try It Now. I already have an account, but if you don't, you can create one with your email or GitHub account. Then I'll click Create a Dataset, and I'm going to call this Aquarium. And the things that I'm labeling are the animals. Then I'll take all my images that I took and drop them into the interface. This will process them, and then it'll let me upload them to my account so I can label them. Now that our images are finished uploading, I just need to go through and put boxes around all of the things that I want our model to recognize. So remember, we're going to label all of the fish, jellyfish, penguins, sharks, starfish, and stingrays. If you don't want to go out and collect and label your own images just yet, you can go to public.roboflow.com to download a pre-labeled dataset that's ready to go so you can follow along with the rest of the tutorial. Now that we've labeled all of our images, we have what's called a dataset. This is analogous to the flashcards from earlier. It's the set of all images and annotations that our neural network is going to use to learn how to identify fish. We'll use RoboFlow's dataset health check to get a closer look. You access the dataset health check on the left-hand side of the dataset page. It gives you all the high-level information about your images and annotations that you'll need to make your pre-processing decisions. So here we have 441 total images, and they've all been labeled. But we also see that one of the images is missing subjects. So this means that we have a photo that didn't have any fish or puffins in it. This is fine. Having a few null examples is actually good. It teaches your model that there's not always going to be something that it's looking for in an image. But if you have too high of a percentage of null examples, your model's not going to learn very well, and you might want to filter some of them out. We also see that we have 3,062 total annotations and 6.9 per image. This is probably skewed upwards by some of the photos of schools of fish that we have. We also see that we have 10 classes, so 10 different types of animals. That's a little bit weird because that's more than we intended to label, and so we'll see in a second if there's something that we have to correct. The other thing we can notice from the top of this page is that our images are absolutely huge. Because we took our training data from an iPhone at full resolution, each picture is 12 megapixels. And that's going to be way bigger than any model is going to be able to deal with. And so we'll want to downsize those later to speed up time at training and also to decrease our file sizes. Next, we'll look at our class balance, which is the distribution of our different types of objects amongst our images. And we can see a few different things from this chart. First, we note that we have way more examples of fish than we have examples of anything else. Sometimes this can be a problem. You generally want your classes to be relatively evenly distributed. And that's because you don't want your model to learn that it should just guess fish because most of the time the thing it's looking at is a fish. You want to force it to also learn things about all of your other classes. There's a few different ways to address this. The best way would be to go back to the aquarium to get more examples of our underrepresented classes. But there's another way called oversampling, which is using your existing images to create more training examples of the underrepresented classes. This is a strategy that we'll cover in a future video. We also have 3 severely underrepresented classes, the humans, the bannerfish, and the turtles. And it looks like two different things happened there. Number one, we split this data set's labeling task amongst the different members of our team. And it looks like somebody didn't get the memo that we weren't looking for turtles. That wasn't amongst the initial list of objects that we wanted to label. So we'll filter those out. Also, it looks like somebody was a bit more specific on labeling a certain type of fish. We actually just wanted to label fish in general, not the different species. And so we'll rename all of the bannerfish labels to fish automatically in just a moment. Finally, it looks like we didn't have enough examples of humans to come up with something that our model is going to be able to learn from. And we actually didn't care too much about finding the humans in the first place, so we'll drop those from our data set as well. Next, we'll look at our dimension insights. And this tells us what the different sizes and aspect ratios of our photos are. So we can see we only have two different sizes of images. This is because we only took photos from one type of camera. If we had taken photos from a whole range of cameras or collected them from a bunch of different people, we might have a whole scattering of different images. For our purposes, it looks like the most important thing is that 436 of our images were taken in portrait mode, but only 5 in landscape mode. And that might lead us to have to restrict our app to only operating in portrait mode because our model isn't going to learn too much about what landscape mode photos look like. Next, we'll look at our annotation heat map, which is a visualization of the position of our object relative to the frame of the photo. And as you can probably expect, most of our objects are congregated right here around the center. If you look at the fish, the starfish, the penguins, they're all kind of in that same spot around the center. It makes sense because when you take a photo of an object, you're going to try and center it in your photo frame. Remember this distribution because in a second, we're going to use this as a trick to improve our model's deployed performance. Now that we know what we're dealing with, we'll go back into the data set and set up our image processing pipeline. We'll apply pre-processing and augmentation steps. These are image processing techniques that are going to transform our images so that our model trains faster and performs better. So the first thing we're going to do is address those problems with class balance that we identified. So we're going to rename the bannerfish to fish. We'll get rid of the humans, and we'll also get rid of the turtles. Next, we'll deal with downsizing those huge 12 megapixel images to something more manageable by our model. You'll want to do some research to see what input size your model takes, but I know that the one we're going to use uses 416 by 416, so I'll choose that. I'll also apply contrast stretching, which is going to let my model use more of the color space. It makes the lightest pixel white and the darkest pixel black. And finally, we're going to apply what we learned from the heat map, namely that our objects appear primarily in the center of the images to crop out the corners and give our model a much higher proportion of content-rich pixels. Next, we'll add some augmentations. This is the process of taking our existing training data and applying transformations to create new training data. It means that we'll get a bigger data set without having to go out and take and label more images. Having a bigger data set is important because it makes it less likely that our model will be able to memorize the exact images that we feed in, and it'll make it perform better when we show it completely new images out in the wild. So we'll go through these settings and apply the ones that seem to make sense to our images. So for example, it doesn't matter if our fish are facing left or our fish are facing right. We might have examples of both of those. So we're going to apply the horizontal flip augmentation, but not the vertical flip augmentation because normally fish don't swim upside down. Now we're going to go through the other augmentation options and add the ones that simulate things that our users might be doing in the wild. So we'll add crop in case they're a little bit closer or a little bit farther away from the fish, or the fish are a bit off-center. We'll add rotation in case the fish are swimming a little bit up or a little bit down, or the person is holding the camera a little bit off-axis. Similarly, we'll add shear to do the same thing as rotation, but on the other two axes of rotation. So the fish might be swimming a little bit towards us or a little bit away from us. And then we'll change the hue a little bit in case the fish are a slightly different color or the coral is a slightly different color. We don't want our model to learn the exact color profile of the exact fish that we took pictures of. Same thing with saturation. In case they're a little bit more vibrant or a little bit more dull, this could also be affected by the lighting conditions. Brightness and exposure also could be changed based on the lighting condition of the particular aquarium and the time of day. So we'll adjust both of those. And then we'll apply a little bit of a blur to some of the photos in case the fish is a little bit out of focus. We don't want our model to be honing in specifically on those crisp lines. And I think that looks like mostly it. We have some of these other advanced augmentations that we're not going to apply for this simple model, but that you might want to check out. And we have some other content that you should look into for specifically mosaic, cutout, and bounding box augmentations. And your problem might be a little bit different, and 90-degree rotation might make sense. For instance, if you're looking at drone photos from above, it doesn't matter whether it's upside down or left or right pointed. And you might want to experiment with grayscale and noise, but we're not going to add those to this data set for today. Now that we've picked all of our augmentation options, we'll decide how many versions of each training image to create. So if I select 3 here, what that means is it's going to take each of my 308 training images, and for each one, it's going to create 3 new versions of it by applying a random flip, random crop, random rotation, random all of the things that I've applied, combine those together to create a unique output. The more examples that I create, the better my model is going to generalize to other images that it's never seen in general, but also the longer it's going to take to train. You might set this based on a number of different things. You might observe that your model's not generalizing very well, so you could boost this and train it again and see if that improves performance. Or you might not have enough training images, and it's way easier to generate augmentations than it is to go out and collect more images. So we're going to try and do 10 examples. So that means it's going to take each of our 308 training examples, apply 10 different augmentations to them, and we'll end up with a data set that at the end has 4,400 different images compared to the 440 that we had originally. Now that we have our settings just the way we want them, we'll go ahead and generate a version. This creates a snapshot in time of our data set. And this does 2 things for us. First, it speeds up the training process because it pre-computes all of the different outputs of the images with the transformations that we have applied. But second, and more importantly, it gives us reproducibility. Oftentimes when you're working on projects, you'll want to try a whole bunch of different models, but you don't want to change a bunch of variables at once. And by tying the image processing pipeline to a single point in time snapshot, it means that you can compare just the changes that you're making in the models and not have to worry about whether the images were processed differently or whether the random values just happen to make one model perform better than the other. To create a version, we just click this button and give it a name. I'm going to call mine Augmented. And then this will spin up a whole bunch of servers in the background to process all of the images. This will just take a few seconds. While we're waiting, it would be a good time to subscribe to the channel. Okay, our images are finished generating. Now for the spot where RoboFlow really shines. We're going to download our dataset in the exact format that we'll need for training. Traditionally, this is the spot where we'd have to open up the text editor and start writing Python. But this is a no-code training tutorial after all. The format we want to use is called CreateML. So I'll select that and I'll download that file to my computer. Next, we're going to take our data set and feed it into a tool called CreateML, which is a no-code training platform created by Apple that takes in a data set and spits out a model that's specifically optimized to run really fast on your iPhone's processor. CreateML is a part of Xcode, which is a free download from the App Store. So if you don't have it already, go to the App Store and download Xcode. Xcode comes with CreateML, so once you've installed Xcode, open CreateML and create a new project. We're going to create an object detector, so select that and give your project a name. You can save it inside of the folder that we just downloaded that has all of our images and annotations. Now we just add our training, validation, and test data from RoboFlow, and we should be good to go. We'll be training a YOLO v2 model, which is the full network. You might also experiment with transfer learning if you have the new version of Mac OS. Once I'm ready, I'll hit train, and that kicks off the training process. This will slow down your computer for the duration of training, and it could take quite some time, so I'm going to leave this running overnight. Okay, it's the equivalent of Christmas morning for the nerds. It's time to check in on how our model did. We left it running overnight, and it looks like it's finished training. So now we're going to see the results. After about 6 hours of training, my model went through all of my images 13,000 times. That's a lot of flashcards. As we can see, the loss value, or the measure of the amount of error that it was getting, decreased over time as we'd expect. It ended up at 1.75, but it's a little bit hard to understand whether that's good or bad without seeing some examples. On the Preview tab, I can see how my model makes predictions. So I'll load up all of the images from my test set to see how it did. Importantly, these are images that my model has never seen before. So here we can see that it found a whole bunch of penguins. That's great. Looks like it found this starfish with 100% confidence. Got those jellyfish pretty well as well. So subjectively speaking, I feel like this model did pretty well. We can also go in here to evaluation and see how it did objectively speaking. This measures the intersection over union, which is the percentage of each bounding box that it predicted correctly. So it looks like it predicted the jellyfish extremely well. Some of the other classes like fish and starfish it did medium on. But the penguins and puffins it did pretty poorly on. If I recall correctly, the puffins were a bit of a weird situation where they had a whole bunch of water splatter on the glass, and I expect that that is why it didn't do very well on those. I'm not sure about the penguins. It might be that there were so many of them in the background. If I was going to go back and try and improve this model, I'd probably go collect more photos of the penguins and puffins to try and improve the performance on these classes. All right, we're almost to the finish line. So far, we've collected images, we've labeled them, we've processed them into a data set, and we've used that data set to train a custom model. Now all that's left is wrapping that model in an app so we can deploy it to our iPhone. Apple's already created a sample app for us. So if we just search for Apple Breakfast Finder sample app, we'll be able to find this sample page that lets us download an Xcode project that's already created for us. So we just hit the download button, and then we'll open this project in Xcode. Once you open Xcode, you'll have to do two things for setup. First, plug in your iPhone and select it as the device that we want to deploy to. And second, go to the signing and capabilities and make sure to set your team here. If you haven't signed up for an Apple developer account yet, you'll have to go to developer.apple.com to create a team. And then the first time you hit this play button, it'll make you authorize your device. Let's see how the model included with the sample app does. It's trained on breakfast items, so I pulled out some bananas, a bagel, and an egg. It looks like it's alright. It's not perfect, but it's passable. So I've got a little bit of a confession to make. I told a little bit of a white lie earlier in this video. I said we wouldn't have to write a single line of code to get things working. But technically, we're going to have to change one or two configuration lines in our Xcode file so that our iPhone will know to look at our new model instead of the example model. Don't worry, we'll walk you through it, and you don't need to know anything about how to code for an iPhone. You can just follow these simple steps, and your model will be working fine. All I need to do is go to the very top left and click the file folder icon to view all the files in this project. We can see that there's an object-detector.ml model file here that's been trained to identify breakfast items. What we want to do is replace this model with our model that knows how to find fish. So if I open back up CreateML and go to the Output tab, I can drag our aquarium1.ml model file here and import it with the default settings. It should show up here on your file browser, and if you click it, you'll see that this model knows how to identify the things that we're looking for. Now all we need to do is update the code to reference this aquarium1.ml model instead of the object-detector.ml model. And that's in this file called Vision Object Recognition View Controller. So if I go in there and look at line 24, I can see that they've referenced object detector here, and we just need to change that to aquarium1. I'll save that file and then hit play, and it'll build this for my iPhone, and now the app is looking for the things in our model, the fish. Success! We've now successfully trained our model on a custom dataset and deployed it to the iPhone. Now all that's left is testing to see how it does. Wow, that's looking pretty darn good. Let's compare those results with a model that I trained with in RoboFlow that's a bit more powerful. You can see that the bounding boxes are a bit more reliable and stable in the RoboFlow trained model, especially when the fish are really overlapping, but they both did a pretty good job. But what happens if we take the app to a different aquarium? Will it still do just as well? Yikes. No, it looks like the model's not doing very well at all. Turns out this aquarium has different species of fish. Let's see what happens if we retrain the model with some new training data. Much better. This just goes to reinforce how important it is to get representative training data. That is, the flashcards that you train your model with should be as close as possible to the images that it's going to see in the wild. Well, that wasn't so hard, was it? We just went through the entire process of creating a custom computer vision project in just a few minutes, and as promised, it didn't even require a PhD. We went out into the field and we collected images. Then we took those raw images, we labeled them, pre-processed them, and augmented them to create a dataset. And then we used CreateML to train a custom model on that dataset and deployed it to the iPhone. The next part's a bit more tricky. You've got to use your human creativity to figure out what project you're going to build next. You can use these exact same steps to do any one of thousands of different things. The only limit is your imagination. And we're really excited to see what you come up with. Be sure to share any cool projects you build in the comments. And if you like this video and want to see more like it, please subscribe and don't forget to ding the bell so you get updates when new videos come out.
Hey there, it's Joseph from RoboFlow. It's Joe from It's Joe from